a03 is going to be a re-implementation of the LCM function in a recursive manner. So the good news is that the test harness is going to be the same. The way that we're going to call it from main.c and test.c is also going to be the same. So we do not change the way the function behaves. We do not change the interface of the function. We change instead the way it is implemented. So let's have a look at truth.c, which is really the only place where we're going to modify something. And I'm going to keep the code from the previous version, but I'm going to call it LCM underscore iterative. Nobody is going to call it, of course, because it's not going to be visible in the .h files, tool.h, and it's not going to be invoked from main.c and test.c, but it's going to be there just for me to refer back to. Okay? So int LCM. So now I'm re-implementing again LCM, but this time I'm going to try to implement it in a recursive manner. So what does that mean, recursive? Well, let me first take care of those little spaces which I forgot here. It's going to be the way otherwise. What does that mean, a recursive function? Well, that means that you're going to call LCM, and instead of using a loop statement of any sort to be able to increment n from 1 to whatever value is needed, we are going to achieve the same result by calling ourselves recursively. So LCM is going to call itself. Let's take a piece of draft paper and try to figure this one out. When I call LCM, I call it with x and y. Okay? What do I expect it to do? I expect it to return to me the least common multiple, of course, but I expect it to do so by calling itself recursively. So I need to identify how I can call myself so that LCM would have to work on a sub-problem. And right now, right here, I can't do that. I can't do that because I have two parameters x and y. Should I call myself by diminishing x, like we do in factorial and Fibonacci, by diminishing y? Do I need to add something to the result of the recursive call? That doesn't fit our problem. So let me try to rephrase our problem here. What if I call LCM with x, y, and a value for n, the smallest value for n, 1. Well, then I have a new function, right? I have a function that takes 3 parameters. And what is this function going to return to me? Well, it depends. It depends of what? Well, if n is the LCM, I return n. So if, what is my condition already? N modulo x equal 0. I'm going to remove this extra parenthesis here in 1 second. Okay. If n modulo x equals 0 and n modulo y equal 0, then I'm returning n, the current value of n. Else, and you see that I'm using here really pseudocode, sort of almost mathematical notation here, because I just want to understand what I have to do first, and then I will work in implementing it, to implement it. So, if n is not suitable, what did I do with my loop? I would increment it. I don't have a loop here. How do I increment? Well, I call LCM x, y, n plus 1. That will delegate the job of testing n plus 1 to this recursive call to LCM. Well, calling LCM is not enough. What do I return? Well, I need to take this call here, move it to the right, and I need to make sure that I'm going to return, oops, that's why I use a lot of slides. My handwriting is not really readable. I'm going to return as result of this recursive call whatever this recursive call returns to me. And this is how we're going to implement our recursive function. Important thing, job to do for you. If you really want to learn, if you just watch this video, you didn't try your hand at the program, etc., well, there's not much I can do to help you. But if you are really trying to learn from those examples, well, first, that means you started by trying to do them yourself. Now you see my explanation. You should pause this video and try to implement it by yourself. And then, once you're done, there's one more thing I want you to do. I want you to trace the execution of this code by drawing its stack, so that you understand exactly what recursion is about. So we are going to go back. It's a good time to pause the video, by the way, right now. So we are going to go back to implementing this, okay? And then we are going to trace the stack and see exactly how it's working. I'm going to go back now to tools.c, which I didn't save. So what did we have in our pseudocode? Well, you will see that when you design recursive function, sometimes you have to do what is called a front end. You have to do a function LCM with only two parameters, which is going to call another LCM function, which is going to take three parameters. This is what we're going to do here first. LCM, how can we call it? Backend maybe, BE. LCM underscore backend is going to be our hidden LCM recursive function, the one that has no header in tools.h, the one that therefore cannot be called directly by main.c and test.c. You see, this is not as good as object orientation, but we can manage to have some things private to our implementation. In this case, the only thing visible is the LCM function. And we call our recursive function here backend function with three parameters. Now let's define it. Int LCM backend, text parameter A, text parameter B, text parameter which I'm going to call N. And then we can start implementing what we're discussing of in our pseudocode. When you do a recursive function, you need to get rid of the cases that are obvious. For example, if, well, what is the obvious case? The obvious case is when we found already what we were looking for. So if N modulo A equals 0 and N modulo B equals 0, then we are done. We have here a situation where we can return N. N satisfies the definition of LCM. Otherwise, what are we going to return? We are going to return, we need to return a value, right? So we are going to return the result of calling ourselves recursively with A, B, N plus 1. And that takes care of our recursive function. Now, so one thing we didn't do so far is the processing of error situation. Well, let's take this code here and let's insert it right here. Why right here? So that we can focus only on the job to be done in our recursive function and take care of a couple of things, a couple of pesky things such as detecting wrong parameters inside of the front end function. So let's have a look at how it looks here. If I have an error, return -1 directly here, otherwise I call my recursive function. My recursive function returns n as soon as the correct condition is met, otherwise keep increasing n and calling itself recursively. Well, this is a good start. Let's save it, and we are going to test it. I'm going to go to Conqueror, and we are going to compile tools.c and test.c. I could test it interactively with the menu. But why would I do that? After all, I have a test suite already that is ready to run there in test.c. Before I can do that, apparently I will have to fix a couple of things here. Implicit declaration of function LCMB. Okay, let me go back to this one real quick. Tools.c line 16. Tools.c line 16. Yes, I call my function before I actually give a prototype for it. So this is not really going to be easy on the compiler. I'm going to put my function before I call it, the definition of the function before its first call. This is going to allow the compiler to know what I'm talking about without me having to add yet another prototype in this file. So I'm going back to Conqueror, try to compile, working fine right now, try to run. A.out doesn't say anything, which means I successfully completed all the tests that I had written in test.c. So you see how there is a benefit to transform your test harnesses into something executable, either with a framework or even by hand yourself by implementing a test.c part of your application. Every time we add new function, every time we change our implementation, we can simply run those tests in 1 second instead of having to key in all those values by hand through the menu. So let's have a look at the final result again, and we are done with this exercise.